Group actions are one of the most important topics of this course, so I'd like to give a little bit of some of the intuition, both behind the definition and how I personally think of them as a geometric group theorist. So, a group action is a rule that says if I take an element of G and an element of some set X, so here G is a group, X is a set, I can assign this to a new element of the set. So in other words, I'm thinking of the group as changing the set X, or I personally like to think of the group as moving the elements of X around the set X. So what this means, so this is a rule that describes how an element of G changes X. So what this means is that we can think of groups either as these sets with structure that we've been thinking of, or we can think of them as functions from the set X to itself. But one point of confusion that I think a lot of us face is that the group action, or the way this rule works, the group action depends both on the set and on the actual rule that assigns how we move the elements of the set. So in our adventure sheet, we'll observe how the set affects how we observe the group action. In particular, we'll look at the symmetric or the dihedral group on 3 elements and what it does to the triangle. But what it does to the triangle can mean many things. We can look at what it does to the vertices of the triangle, but we could also look at what it does to the edges of the triangle. So we have a few options for X. We could have that X is equal to the vertices. We could also have that Y, another set that D3 might act on, is equal to the edges. We could further say that Z is the faces of the triangle. There's only one, but D3 acts on the face of the triangle. It takes it to itself. So any one of these are possible sets that D3 could act on. And the results that we'll get if we look at the action of D3 on any one of these sets are different. By the way, I'd like to introduce notation for group actions that I like to use, which is a group G acting on a set X is sometimes denoted by G and then this sort of curved arrow X. I like to use that notation. Okay, so I'd just like to highlight a sort of correspondence between groups and group actions. So groups and group actions. When we look at groups, we maybe look at the elements of the group. And each element of the group corresponds to a particular group action, which we saw in our reading is called ADG. And ADG is a function from the set X to itself that's defined by sending X in X to G dot X, dependent on whatever this group action is. And there's a set of group actions that are particularly nice group actions, which again sort of depend on the group, but they really depend on how the group interacts with the set X. These nice group actions are often called faithful, or not are often called, are called faithful actions. Where a faithful action is one where this map is injective, and we'll see this on our adventure sheet. And we will see on the homework that there's also this nice correspondence between Lagrange's theorem for groups and what's called the orbit stabilizer theorem. For group actions. So in summary, a group action on a set allows us to see the group as a set of functions from the set to itself, in particular a set of bijections from the set to itself. Therefore, if we can find the right set, we can study any group as functions. And there's a lot of advantages to this. But one of the areas of research math is actually finding the right set for a group to act on. This isn't obvious in general. And so it's a really beautiful and rich intersection between group theory and geometry.